usul untuk bergabung ya. Ya alhamdulillah kita masih dalam keadaan sehat ya hari ini. Mudah-mudahan semua juga dalam keadaan sehat. Ya ini kode untuk kuliah kita hari ini, silakan dimasukkan. Kemudian untuk slide juga sudah diupload ya untuk pertemuan pertama dan kedua, jadi nanti bisa di-download. Nah sekarang saya akan coba, kita akan coba masuk ke materi. Saya akan coba share slide ini sebentar. Sebentar. Ya mudah-mudahan ini sudah muncul ya, sudah tampak ya. Oke. Jadi ini adalah yang kemarin kita pelajari pekan lalu ya. Jadi kita akan memberikan sedikit review tentang apa yang sudah kita bahas. Sebetulnya pekan lalu hanya introduction saja ya. Apa sebetulnya yang kita pelajari di dalam analisa numerik ya, yang mana pada intinya kita akan menyelesaikan suatu problem matematis ya yang kita dapatkan dari teori dengan pendekatan yang berbeda dengan apa yang sudah kita pelajari di kalkulus. Nah, jadi seperti yang sudah kita lihat di contoh pekan lalu ya, yang mana kalau kita punya persamaan matematis ya, yang mana kita dapatkan dari mencari kesetimbangan gaya di sini, maka kita bisa mendapatkan hasil analitis ya dengan melakukan pengintegralan terhadap persamaan tersebut, dan hasil analitisnya adalah persamaan eksponensial yang ditunjukkan di sini. Nah, kemarin kita juga sudah melihat bahwa ini dalam kasus ini ya kita perlu melakukan perhitungan kalkulus untuk mengintegralkan, yang mana untuk kasus ini masih memungkinkan karena persamaannya tidak begitu rumit. Nah, tetapi ketika makin kompleks ya, maka kadang-kadang sulit kita melakukan integrasi ya, kadang-kadang sulit kita melakukan integrasi. Sehingga di dalam analisa numerik kita lakukan pendekatan yang lebih sederhana ya, lebih sederhana, sangat mudah begitu ya, di mana gradien itu, atau kalau kita punya gradien itu dikatakan sebagai slope ya, dv per dt atau garis singgung, maka itu didekati dengan delta v dibagi dengan delta t, begitu saja. Di mana delta v itu adalah selisih, dalam hal ini adalah selisih antara kecepatan pada posisi waktu i plus 1 dikurangi dengan waktu kecepatan pada waktu i dibagi dengan delta t-nya, yaitu t i plus 1 dikurangi dengan ti. Seperti itu saja. Dan ini kita masukkan ke dalam persamaan, kita putar saja ke sisi keruas kanan, maka akan jadi seperti ini. Jadi secara umum di sini kita dapat dengan mudah menghitung ya, istilahnya marching, maju ke depan begitu ya, marching itu maju ke depan. Dari nilai lama kita bisa mencari nilai yang lebih baru begitu. Jadi nilai baru dihitung dari nilai lama ditambah dengan slope ya, dikalikan dengan jaraknya, marchingnya berapa, step size-nya, seperti itu. Nah, ini pendekatan yang sangat sederhana begitu ya. Jadi tidak perlu melakukan integrasi. Nah, tentunya di sini ada perbedaan antara real slope, yaitu garis singgung yang sebenarnya. Jadi seumpama kita punya suatu persamaan yang realnya adalah semacam ini, ditunjukkan oleh garis hitam ya, ditunjukkan oleh garis hitam. Data poinnya pada titik TI dan TI plus 1 diketahui ya. Nah, maka real slope atau garis singgung sebenarnya itu ditunjukkan pada yang atas ini. Nah, sedangkan kalau kita menggunakan pendekatan aproksimasi tadi ya untuk slope itu yaitu dV per dt diganti dengan delta V per delta T, maka slope yang kita dapatkan sekarang hanya garis linear yang menghubungkan antara kedua titik tersebut. Jadi kita lihat di sini memang ada perbedaan dan inilah nanti yang menjadi error ya. Karena kita sederhanakan. Nah, maka dari situ kemarin kita bisa melakukan time marching ya, kita masukkan dari 0, 2 detik dan seterusnya sehingga kita dapatkan kecepatannya dan kita bisa plotkan hasilnya. Sehingga dari sini kita lihat ya bahwa memang ada perbedaan antara approximate atau hasil dari numerik dengan hasil eksak atau analytical solution-nya. Ya, yang mana di sini ya goal kita adalah seperti yang sudah kita bahas pekan lalu, yaitu meminimalkan errornya, membuat kita berusaha menggunakan metode ya yang sebisa mungkin ini errornya tidak besar gitu ya. Jadi sebisa mungkin kita reduksi errornya, kita minimalkan errornya. Nah, maka ada beberapa cara untuk mendapatkan itu ya, tergantung pada beberapa faktor. Untuk kasus ini saja ya, misalkan kita bisa menggunakan pendekatan yang berbeda. Kalau tadi itu katakanlah kita punya grafik semacam ini ya. Ini tadi kita ambil aproksimasinya untuk gradien pada titik I ya atau garis singgung pada titik I yaitu dengan menghubungkan pada titik sesudahnya. Bisa juga kita menggunakan pendekatan yang lain, misalkan saya ingin menghitung gradien di sini, yang saya pakai bukan titik sesudahnya tetapi titik sebelumnya. Begitu. Jadi misalkan saya punya TI-1, TI-1 di belakangnya misalkan seperti ini. Nah, maka di sini saya akan menghubungkan, katakanlah ini garisnya semacam itu, maka saya akan menghubungkan antara titik tersebut ya, antara TI dengan TI-1, maka inilah slope yang saya dapatkan. Seperti itu. Nah, itu adalah salah satu alternatif atau misalkan centered ya di sini. Centered artinya kita menggunakan titik yang lain. Ya, kita menggunakan titik yang lain dalam mencari gradien. Seperti itu. Jadi pendekatan untuk menghitung gradien ini ada beberapa ya untuk menghitung garis singgungnya. Nah, inilah metode-metode yang ada dan kita akan bahas ya perbedaannya seperti apa, mana yang lebih baik untuk kasus kita. Kemudian juga berapa step size-nya ya. Kalau tadi ini dicontoh digunakan setiap 2 detik. Nah, apakah kita bisa mereduksi error misalkan dengan membagi menjadi setengahnya delta T-nya. Jadi kita melakukan perhitungan setiap 1 detik misalkan. Nah, setiap 1 detik kita hitung. Nah, kalau dari sini secara logika ya, kita akan dapat meminimalkan error begitu. Kenapa kok bisa meminimalkan error? Karena gradien akan dihitung per titik ya, per titik seperti itu. Jadi kalau kita menggunakan step size yang lebih kecil ya, maka di sini gradien akan dihitung ulang setiap 1 detik. Maaf. Ya, jadi akan dihitung ulang setiap 1 detik. Jadi di sini kita lihat di sini maka akan semakin mendekati ya, karena dihitung ulang per 1 detik. Maka akan meminimalkan error ya. Jadi itu salah satu lagi faktor yang bisa kita tentukan ya untuk meminimalkan error. Kemudian 1 side atau 2 side, forward atau backward, ya pendekatan ke arah depan atau ke arah belakang, atau 2 sided, 2 sided. 2 sided artinya kita menggunakan titik baik yang di depan maupun yang di belakang. Seperti di sini contohnya adalah center, ya. Jadi kalau center bagaimana? Misalkan saya punya kembali lagi seperti tadi, kita punya suatu kurva. Nah, kemudian yang saya ambil untuk mencari garis singgung di sini, katakanlah ini garis singgungnya pada I, maka yang saya ambil adalah dengan menghubungkan 2 titik sesudah dan sebelumnya. Jadi I plus 1 dan I min 1. Jadi kalau kita tarik kemari, ya, maka kita hubungkan kedua titik ini. Ya, nah ketika menghubungkan maka nanti bagaimana tangent line-nya, maka ini menjadi delta Y-nya, dan ini adalah delta X-nya. Maka delta Y-nya adalah Fxi plus 1, yaitu nilai di sini, dikurangi dengan Fxi min 1, yaitu di sini, dibagi dengan delta X. Delta X-nya sekarang ada 2 kali H. Ya, karena 1 H itu adalah dari I plus 1 ke I. Ya, ini juga H. Jadi total jaraknya nanti adalah dibagi dengan 2 H. Maka kita perhatikan di sini kalau center kita hubungkan antara 2 titik di sebelah kanan dan sebelah kirinya. Nah, Nah, kemudian pertanyaan berikutnya, berapa optimal step size-nya? Berapa step size yang harusnya kita gunakan supaya hasilnya presisi, ya? Kemudian formulanya bagaimana? Nah, ini adalah faktor yang kita perkembangkan dan ini sebetulnya main goal-nya ya dari analisa numerik ya. Jadi memilih metode. Baik, jadi itu adalah bab 1 ya. Nah, kemudian bab 2 ini kalau kita lihat di buku ya, itu mengenai programming dan software. Jadi kalau kita lihat buku nanti memang cepat sekali kita ya, mohon maaf ini tadi sepertinya saya terputus ya. Sebentar. Coba saya share lagi. Ya. Baik, jadi bab 2 di buku itu adalah tentang programming dan software ya. Karena di sini saya tidak akan membahas terlalu dalam karena ya pastinya semua sudah lulus algoritma pemrograman ya. Jadi basisnya juga salah satunya adalah bahwa kita akan mengaplikasikan pemrograman ya sedikit. Jadi nanti insya Allah ada membuat program sederhana untuk mengaplikasikan metode numerik ini di komputer ya. Jadi secara umum ini review saja ya apa yang sudah kita pelajari dulu. Programming itu ada dua macam, ada structured dan modular. Ada apa bedanya ini antara structured dan modular? Mungkin ada yang mau menjawab?
Bu, permisi mau menjawab.
Ya, silakan Sultan.
Kalau structure itu mungkin apa namanya kayak cuman programming yang cuman beberapa input cuman buat satu tujuan, tapi kalau modular programming itu ada banyak modul di situ, Bu. Jadi kayak ini satu program tapi bisa digunakan untuk banyak sekali tujuan atau banyak sekali output. Kalau structure itu cuma satu. Kalau pendapat saya begitu, Bu.
Ya, baik. Ya, jadi kalau structured itu hanya satu tadi ya disebutkan hanya satu, kalau modular hanya ya. Ya, sebetulnya modular pun juga bisa digunakan untuk satu macam software ya, misalkan satu macam program. Tetapi memang keuntungannya adalah bisa digunakan berkali-kali untuk program yang lain juga ya. Ya, jadi secara umum tadi sudah betul apa yang disampaikan ya. Kalau terstructured itu ya sebetulnya setiap program itu terstruktur ya, seperti itu berurutan, ada sequence-nya, ada urutannya, kemudian nanti di dalamnya ada selection ya, ada pilihan, kemudian juga ada looping, pengulangan atau repetition. Nah, itu semuanya termasuk structured programming. Kalau modular ini memang sesuatu yang sedikit lebih kompleks di mana kita membuat modul ya atau suatu bank begitu ya, bank yang berisi sejumlah instruksi yang akan digunakan berulang kali begitu ya. Jadi isinya adalah function di situ ya, di dalam modul itu isinya adalah berbagai function yang mana nanti function ini bisa digunakan berulang kali baik pada satu program maupun program yang lain begitu ya. Jadi selama kita modul itu kita ikut sertakan ya di dalam program kita, maka kita bisa memanggil fungsi-fungsi yang ada di dalamnya. Ya, jadi tadi jawabannya sudah betul. Kemudian flowchart dan algoritma, apa bedanya antara keduanya ini? flowchart dan algoritma. Perbedaannya apa?
Bu, mungkin untuk kamu jawab lagi.
Iya.
Kalau
Gimana?
flowchart itu kayak rincian alurnya. Jadi
Mm-mm.
dari proses awal ke akhir itu alurnya dirincikan di flowchart. Kalau algoritma itu lebih ke banyaknya caranya, Bu. Ini ada berapa cara yang bisa digunakan untuk dari satu form ke form lain, dari satu input ke output. Itu kalau caranya itu algoritma.
Iya. Iya. Ya, sebetulnya sama ya antara algoritma dan flowchart itu sama ya. Jadi sebetulnya hampir sama, cuma mungkin algoritma ini lebih dalam bahasa yang berurutan begitu ya. Jadi dalam bahasa yang berurutan. Isinya sama sebetulnya step-step juga begitu ya. Tahapan-tahapan. Tapi mungkin lebih lebih bersifat lebih umum begitu ya. Mungkin tadi disebutkan mungkin bisa ada banyak cara begitu ya. Jadi bersifat lebih umum yang mana itu nanti menggait pola berpikir. Kalau flowchart itu dalam bentuk diagram ya, seperti yang kita lihat di sini ada simbol-simbol yang digunakan di dalam diagram. Nah, flowchart ini biasanya lebih mudah dipahami ya, karena kalau ada pengulangan ya, ada looping seperti itu akan terlihat lebih jelas dengan adanya flowchart. Sedangkan kalau algoritma di sini ya bisa kita tuliskan ada pengulangan, tapi mungkin lebih sulit ya ketika kita membayangkan seperti itu. Nah, tapi sebetulnya intinya sama ya. Jadi ada proses alur ya, alur penyelesaian ya, ada alur penyelesaian, sama juga algoritma juga demikian ya. Yang pada intinya adalah bagaimana caranya atau apa instruksinya nanti yang perlu dilakukan oleh komputer untuk mendapatkan solusi. Seperti itu. Nah, nanti dari flowchart dan algoritma ini nanti kita buat pseudocode, yang mana pseudocode ini sebagai pengarah ya ketika kita membuat kodenya. Ya, jadi pseudocode itu sudah mirip dengan kode, cuma mungkin dalam bahasa yang lebih umum ya. Kalau coding itu sudah sintaksnya harus sesuai begitu ya. Nah, mungkin kalau dulu sudah pernah belajar Python ya, membuat kode dalam Python, maka tidak ada masalah untuk mengaplikasikan di dalam MATLAB ya. Karena MATLAB pun itu juga ada bisa diinterfacekan dengan Python. Jadi secara umum sebetulnya semua program bahasa pemrograman itu pada intinya adalah sama, yang mungkin sedikit membedakan hanya sintaksnya aja, tata cara penulisannya. Tapi semua pada intinya konsep berpikirnya ya itu kurang lebih adalah sama. Baik, jadi itu tentang bab 2 ya, yang mana saya tidak akan membahas terlalu dalam di situ. Nah, sekarang kita masuk ke bab 3, yaitu mengenai salah satu error yang disebut sebagai roundoff error ya. Dan ini penting karena kita melakukan aproksimasi, pendekatan ya. Maka seperti yang kemarin sudah kita ingat bahwa kalau aproksimasi mesti ada error selalu ya. Tidak mungkin tidak ada, ya namanya aja pendekatan. Tidak ada ketika kita bisa membuat persamaan yang betul-betul sesuai ya, ketika kita menggunakan persamaan yang betul-betul sesuai dengan exact solution. Dalam hal itu juga kita tidak perlu melakukan aproksimasi begitu ya. Nah, jadi selama kita menggunakan approximated value, maka error itu mesti ada. Dan error itu ada dua macam ya, ada dua macam. Nah, kemarin sudah kita bahas ya sepertinya. Error itu ada dua macam. Oke. Jadi terkait dengan error ini, maka di dalam analisa numerik kita perlu mengidentifikasi error. Ya. Jadi kembali lagi ke metode numerik ya. Pada intinya adalah kita tidak menggunakan ya perumusan yang sudah kita pelajari sebelumnya. Contohnya ya, misalkan di sini kita punya pengintegralan dari 1/x dx dengan limit dari A ke B. Ya. Nah, ini di sini kalau ini penyelesaian secara kalkulus biasa, maka kita tahu 1/x itu integrasinya apa? Ln x begitu ya. Batasnya dari mana? Dari A ke B. Maka hasilnya nanti jadinya ln B dikurangi dengan ln A. Oke. Ini sudah relatif mudah ya. Ini relatif mudah. Tetapi kita harus punya pemahaman lebih dulu ya, kita harus punya pengetahuan lebih dulu bahwa bagaimana integral dari 1/x. Ya, misalkan. Atau misalkan ini saya ubah sedikit tidak 1/x tapi 1/1 min E pangkat X. Misalkan. Seperti apa? Sudah mulai lebih kompleks. Atau tidak begitu, atau 1 per X dikurangi E pangkat X. Lakukan integral. Nah ini mungkin bisa ya, tapi butuh berapa lama begitu ya. Nah ini mungkin sudah mulai kita bagaimana cara melakukannya. Apakah bisa kita dapatkan integrasinya dari sini? Nah maka di sini analisa numerik menggunakan pendekatan yang lain. Kita kembali lagi ke basic tadi ya, seperti yang sudah kita bahas lalu ya, pekan lalu. Kalau kita punya suatu fungsi, katakanlah ini XF ya fungsinya. Nah, maka ketika kita punya pengintegralan, itu sebetulnya adalah mencari area di dalamnya. Ya, seperti itu. Maka apa yang kita lakukan, kita dekati dengan salah satunya adalah dengan metode trapezoid. Trapezoid itu apa? Trapesium ya. Jadi pada intinya kita bagi aja, kita bagi menjadi elemen-elemen kecil di sini, bagian-bagian kecil. Kemudian kita dekati aja, kita cari poin di sini berapa, poin di sini berapa, begitu ya. Kita asumsikan ini adalah area trapesium begitu. Kemudian kita jumlahkan, sudah begitu saja. Tidak ada perhitungan yang sulit ya. Nah, itu yang dilakukan oleh analisa numerik. Tapi tentu saja ya, karena ini semuanya kita dekati, semuanya dibuat lebih mudah, maka mesti ada error. Contohnya di sini ya, ini kita dekati dengan satu garis linear ketika menghubungkan titik di sini. Padahal sebetulnya tidak linear kurvanya. Nah, ini adalah sumber-sumber dari error. Maka itulah yang akan kita lakukan dalam analisis ya. Salah satunya adalah analisis error, yaitu mengidentifikasi apa penyebab error itu. Jadi kalau kita punya error, kita harus paham dulu errornya ini munculnya dari mana. Ya. Apa penyebab munculnya error. Kemudian juga kita harus tahu cara menghitung error. Nah ini yang akan kita pelajari. Seberapa besar error itu? Berapa persen? Ya. Nah kemudian terakhir adalah meminimalkan dan mengontrol error tersebut. Ya. Jadi dari problemnya apa, penyebabnya apa, besarnya berapa, dan bagaimana menguranginya. Itu yang disebut sebagai error analysis. Dan itu yang akan kita aplikasikan. Jadi tidak sekedar mengaplikasikan metode, tapi juga melakukan analisis, karena itu namanya analisa numerik ya. Jadi melakukan analisis apakah ini acceptable atau tidak, bisa diterima atau tidak, ya, sudah cukup baik atau tidak pendekatan yang kita lakukan. Nah, ini salah satu contoh ya di mana kita bisa meminimalkan error. Ini adalah contoh yang tadi ya, yang kasus parasut tadi ya. Yang mana kita punya exact solution yang ditunjukkan oleh garis biru, kurva biru di situ. Dan garis merah ini adalah yang sudah kita dapatkan dari perhitungan sebelumnya dengan delta T 2 detik begitu ya. Nah, ternyata dengan mengurangi step size ya, dengan mengurangi time step-nya yang awalnya 2 detik, sekarang kita kurangi menjadi 1 detik. Artinya gradien itu diupdate setiap 1 detik. Sehingga karena diupdate lebih sering, maka penyimpangannya juga akan lebih kecil, begitu ya. Penyimpangannya akan lebih kecil, sehingga kita perhatikan di sini untuk delta T 1 detik, di sini garisnya semakin mendekati exact solution. Seperti itu ya. Jadi kita punya bayangan di sini, oh ternyata ini kita bisa kurangi. Nah, apa kalau kita mau kurangi lagi, kita coba buat setengah detik, mungkin bisa lebih mepet lagi, ya, lebih mendekati lagi, lebih rapat ke exact solution dan seterusnya. Nah, ini adalah salah satu cara untuk meminimalkan error. Ya. Nah, terkait dengan error ini harus kita pahami bahwa ada 2 jenis error, ya, ada 2 jenis error. Ya, yang pertama adalah rounding, yang kedua adalah truncation. Nah, ini bisa dibaca sendiri definisinya ya. Rounding kalau di sini dikatakan terkait dengan kemampuan komputer ya dalam mendefinisikan suatu angka yaitu finite representation. Jadi apa di sini maksudnya rounding error? Finite itu berarti terbatas ya. Ya, gimana Abi?
Mungkin kalau misalkan angka yang diperlukan itu memiliki banyak desimalnya, Bu. Nah, komputer tuh cuma bisa mendeteksi desimal yang kedua, jadi dibulatkan ke atas gitu, Bu. Jadi desimal yang lebih kecil lagi hilang.
Ya, betul. Ya, jadi karena terbatasnya jumlah angka yang bisa disimpan oleh komputer. Betul sekali ya. Jadi itu kaitannya dengan itu. Maka ada error yang disebut dengan rounding error. Biasanya kita sebut pembulatan ya. Jadi contohnya nanti kita akan lihat angka-angka yang terlalu panjang, katakanlah apa paling mudah sejarahnya pakai komputer, pakai kalkulator ya. Pakai kalkulator misalkan 10 dibagi 3 itu kan 3,333 dan seterusnya begitu ya. Nah itu pasti ada dipotongnya begitu ya, karena itu sampai tak terhingga nanti ya. Maka angka itu dipotong ketika disimpan, karena memang ada keterbatasan. Nah nanti kita akan lihat seberapa angka yang mampu disimpan oleh komputer. Ya. Jadi itu sudah betul. Nah yang berikutnya adalah disebut sebagai truncation error. Nah ini dibaca apa maksudnya truncation error di sini ya. Jadi kalau kita perhatikan truncation error ini akibat, maaf saya lupa ini kelas Y ya, mestinya berbahasa Inggris. Ini saya tidak ada yang ingatkan jadi bahasa Indonesia terus. Oke, switching to English ya. Tolong saya diingatkan kalau lupa karena tadi juga barusan mengisi dalam bahasa Indonesia jadi lanjut ini bahasa Indonesia terus untuk sesi keduanya. Baik. Oke, switching to English ya. So we have truncation error. So if we see the definition here, yeah. So truncation errors is due to differences between the exact and the approximate or numeric formulation of the mathematical problem being dealt with. So what do you have in mind when you read of this definition? So there is a difference, yeah, between the exact and the approximate formulation of the mathematical problem being dealt with. Yeah.
Excuse me, I want to try to answer it. I think it's like a gap between the approximate slope and exact slope. If you like it.
Yeah, so that is correct. Yeah, so this is dealing with the simplification. Yeah, dealing with the simplification of the formulation. So such as what we've seen before, yeah. So if we have a graph and we have the real slope, yeah. So we have seen in the parachutist problem that we simplify the calculation of the real slope with connecting the points with linear lines. So this is the main source of truncation error. So it's dealing with how we simplify the equations into very simple formula, such as linear line. Yeah. So we should remember that we have two errors, yeah, and this will contribute. These two errors will contribute to the total error of our calculations. So we should remember that we will have rounding and also truncation error. Okay, so we will discuss the first, yeah, which is about rounding errors, and later we will talk about truncation error. So rounding error here, we will see how we store the number in the computer. Yeah, so perhaps if you were in my class taking algorithm and computer programming, yeah, so you might have seen this before, yeah. So this is about how the computer stored a number. Yeah, so this is called significant figures, or you can say significant digits. How many digits that can be stored by a computer? Yeah. So we see here that, for example, we have pi. Yeah, a constant pi. So pi here is 3.14159.265 and so on. Yeah. So sometimes it's very long. It has very long digits, so that we have to store only few significant numbers. Yeah. Or for example, here we have the second example is the square root of 17. Yeah. So the result will be 4.123 and so on. So it can be a very long number. Yeah. But there is a limitation of the computer. So dealing with this, we will see again of the definition of accuracy and precision. Yeah. And I think we have discussed about that as well. Yeah. Last week. And you have answered this correctly, in which what is an accuracy? Yeah? So it's dealing with how close it is. Yeah, how close is our solution, our numerical solution, to the true value. Yeah. So the opposite of accuracy is inaccuracy or bias. Yeah, so this is the opposite. So if we have a term of bias, it means that is a deviation from the general trend or from truth, yeah, from the real trend. Yeah, so this is a bias. While precision, as what we have discussed last week, is the closeness of the computed values with each other, or we can say that the spread or the scatter of the data that we have. Yeah, the spread or the scatter of the calculation that we get from numerical analysis. And this precision is really, yeah, it's related to the number of significant figures. So that, yeah, this is very close to have a close relation with significant figures that can be stored by the computer. And in turns, this will also affect the accuracy of our solution. So if we have the term precision, so the opposite will be imprecision or uncertainty. Now you might have learned about this before in statistics. Yeah. So in statistics we have spread and we have uncertainty. Yeah. And for example, we have normal distribution and so on. Yeah. So probably you will learn that as well in statistics. Yeah. Okay. So yeah. So if we look at the illustration, for example, here, yeah, we have a case, for example, we do shooting or archery, for example, yeah, and we have the target here. So what we want is actually getting to the bullseye of the target, yeah. So in the center of the target. So if we look about accuracy, is that accurate means getting into the bullseye, yeah, or getting into the center of the target. So that is increasing accuracy. But dealing with precision is that when we do the several attempts, yeah, so that the result will get into the same location. Yeah. So for example, here we have case A. Case A here is not accurate because it's quite far from the target. Yeah. From the center of the target. And the data we see here is scattered all way around the area here. While in B, we see that the data is still scattered, but this data is still getting close to the center of the target. So it's better, yeah, in terms of accuracy. But both here still have a scattered data, scattered value, yeah, scattered location. While if we increase the precision, so for example, C here, yeah, problem C is one case in which it is a precise calculation, have high precision, but it's not accurate. Yeah. So we do several attempts, yeah, but the value is not accurate. All of those values is not accurate, although it's getting to the same value over and over, but it's not getting to the target that we want. And this is the ideal one, yeah, in which we have the accurate and precise solution. So we do several attempts, it's still getting in the same value, and that value is the accurate value, the real value that we want. Yeah. So that what we want to have is a numerical method that will be sufficiently exact, so without bias and precise. So the goal is figure D here. Yeah. Now to get that, again, we will look at two sources of error, yeah, which is the rounding error first, yeah, and how to calculate the magnitude of the error. Yeah. So before we discuss about rounding error, yeah, so there are two ways of calculating the error. The first one, we call it as a true error, yeah, the absolute error or the true error, yeah, absolute error. So the absolute error is the difference between the true value and the approximated value. Yeah. So for example, we have the analytical solution. So the analytical solution will be the true value. And what we have will be from numerical analysis will be the approximated value. So the absolute error is the difference or the deviation to the true value. So it's equals to true value minus approximate value. Now, sometimes using absolute error is not very representative because we don't know how much it is, how much is the difference to the actual one. So it's easier to define it in percentage. Yeah? So if we want to do it in percentage, so that we use the relative error. So this is called as the relative true error. Yeah. So this is called the relative error, or sometimes we call it the relative true error. Yeah. It's the same, yeah, the relative error or the relative true error. So that will becomes the absolute error, which is normalized with the true value. Yeah, so we normalize it to the true value and multiply it with 100%. So with this, for example, we know the difference, for example, is 5%, or it means that we have a 5% difference between the approximated value to the true value. Yeah. But sometimes, sometimes we don't know the true value, for example. Yeah. For example, the only solution that we have is only from numerical value. So in this case, we can use what is called as A. So this will be the approximate error. Yeah, the approximate error. So what is meant by approximate error? The approximate error, yeah. So this one, this will be the relative approximate error, in which we calculate the relative approximate error is from the approximate error to the approximate value. So both of this value are obtained, are obtained from numerical method. So how can we get the approximate error? Is that we're comparing, between one result, one approximated value to another approximated value. Yeah. So what we have here is, for example, we have the calculation of the relative approximate error will be equals to actual approximation minus previous approximation over the actual approximation. Or for example, if, say we do several iteration, for example, so that we can calculate the absolute error will be the value, the new value, of our iteration minus the old value, over the new value. And this will be in percent, times 100%. So this is how to calculate it. In the case we don't have the true value, so that we cannot calculate the relative true error. We cannot calculate the absolute error. So this is the best that we can do. So we can calculate the approximate error, and this is common. This is common. Okay. So we have known how to calculate the error. And for example, if we do iterations, so that we have to give a criteria in which when the iteration stops. So here we can give a prefix, percent tolerance, or the limit, in which the calculation can stop. So this is epsilon s, for example. If it's below 5%, so that it means that the calculation is already reached. So the solution can be extracted, so that we stop the calculation. And how is the value of epsilon s, or the tolerance that we give? So this depends on the problem. If we want to be very accurate, perhaps 0.1%, or 1%. Sometimes it can be less stringent, for example, 5%. So this depends on us, on prescribing the value of epsilon s. Okay, so that as we see the calculation of the magnitude of the error here, so that we will continue on looking of one of the error, one type of the error, that will contribute. We see here that, for example, yeah, we have a number, say we have 86,409. So this is actually in 10 pieces, yeah, 10 pieces. So that it means that 9 is actually 10 to the power of 0 times 9, yeah. So 9 times 1. 0 here means 0 times 10, yeah, 10. So that will be 0. And then 4 here is actually 4 times 10 to the power of 2, which is hundreds. So that will be 4 hundreds, thousands, 10 of thousands, and so on. So that we have this number, which is 68,409, is actually we get it from 10 bases. Now the computer do not store that. Yeah, the computer has different bases, so it's using binary digits. Yeah, it means it's using 2 as a base here, so not 10. So it's 2. And if we remember of how the computer is, yeah, so the computer is actually consists of transistor. Yeah, transistor. So transistor is only like you have a circuit, and then whether you have an open or closed circuit, like that one. So actually, computer consists of that. Yeah, so it's electrical circuit in which, so that what computer store is only 1 or 0. 0 means it's not connecting, while 1 means that it will connect it. Yeah, it will be connected, so it's connected. So this will be 1. So that say we have a number here, and we store it in binary digits. For example, we have 8 bits here. Yeah, it means that one number will be stored using 8 binary digits. So we have 1, 2, 3, 4, 5, 6, 7, 8. Yeah. So that, for example, here we have 1, 0, 1, 0, 1, 1, 0, 1. So this is what is stored by the computer. So what is the value is actually for us. Yeah. So the value is actually 173. Yeah. So we have 1 times 2 to the power of 0, which is 1. So that will be 1. And then 0 times 2 to the power of 1, which is 0. And then we have 1 times 2 to the power of 2, which is 4. And then we have, and so on. 1 times 2 to the power of 3, which is 8. So that we have 8. And then we have 0 times 2 to the power of 4. So that will be 16. So this is incorrect. Yeah, this should be 0. And then we have 1 times 32 to the power of 5. It's 32. And then we have 0 times 2 to the power of 6, which is 64. So that will be 0. This is incorrect, yeah? So that should be 0. So that we have the last one here is 1 times 2 to the power of 7, to the 2 to the power of 7, so that we have 128. So then if we do the summation, yeah, so that will be 1 plus 4 will be 5. 5 plus 8 is 13. 13 plus 32. 13 plus 32 is 45, yeah? 45 plus 128, so that is correct, 173. So this is the number for us. So when we instruct the computer to store a number 173, so then in 8 bits computer, it will be stored as this one. Yeah. So this is how the computer store the number, yeah? Now, how will it affect our calculation? So we will see here that, yeah, for example, we have 8-bit computer, yeah. So that with this possibility to store the number, yeah, so that we can only represent a finite number in our case from minus 127 to positive 127, or if we have from 0, so that will be 255 number. So if we want to store an integer number in 8 bits, we only limit it to this value. Yeah, so that we can further increase the number of bits. So say we have a computer of 16 bits now, the integer that can be stored will be ranging from minus 32,000, yeah, about minus 32,000 to positive 32,000. Now we don't use 16 bits, yeah, at the moment, yeah. But this is how to roughly how to get the value. And what if we want to store floating number? Yeah, floating number, or we want to store decimal number. Yeah, before this is integer. So integers means that is a value, an integer value, while in decimal we have the floating number. And how we store the floating number in computer is that we use several digits. For example, the first digit will be the sign of the number, whether it's positive or negative value. And then the second digit will be the exponent sign, because we have m times p to the power of e. So the exponent sign of e here will be stored in the second bits. And then we have the magnitude of the exponent. So how much is the value of e, the magnitude of the exponent, and also the mantissa. So the mantissa is actually the value of m here. So the fraction part, the digits that we will store the value here is called the mantissa, the fraction part. So say we have 32 bits, for a bit older computer. So that from IEEE, so 1 bit will be the sign of the value, and then 8 bits for the components, and 23 bits for the mantissa. This means that we will have 23 significant digits for the mantissa. And if we have double precisions, this is common, nowadays, 64 bits. It's 2 times 2 words of 32 bits. It means that we will use 1 bit for the sign, 11 bits for the component, and 52 bits for the mantissa. So more than twice of what we have in 32 bits. So that's why 32 bits is usually called as single precision machine, while 64 bits is often called double precision machine. And if you will do calculation, for example, simulation, using, for example, later using finite element analysis or using CFD, for example, in the software, commonly they provided in what calculation you want to do, whether it's in single precision or in double precision. So we will see that with double precision, so the value that we will store will be more precise, so that we can also reduce the error, so we can also reduce the error. So from here we can see that 64 bits is not only for gaming, but for calculation, the effect will be significant. Okay, so this is the illustration, for the bits that are used for single and double precision machine. So that if we insert the value, so that if we insert the value, so that will end up with this, so that in single precision, so that will be 7 significant digits, so that will be 7 significant digits. So this is the range of the number that can be stored by the computer. So that will be 7. So 1, 2, 3, 4, 5, 6, 7. So this is for single precision machine. 7 digits, 7 significant digits with the mantissa, the exponent from -38 to +38. While if we have double precision machine, we calculated in double precision, it means that we will have 15 significant digits. So then we have 1, 2, 3, and so on, up to 15 significant digits. And the exponent, here can be from -308 to +308. So you will see here the difference is very significant. So we will see later that how can this affect the calculation. Significant digit is very important as well. We might think that for us there is no difference between, for example, using 5 significant digits or 6. But we will see later that the rounding that is caused by limited significant digits that can be stored by the computer will later be accumulated, and that will be carried on into the next calculation, so that if we want to minimize the error, so that the chosen of significant digits will also affecting our calculation. And most of the machines, use chopping. Yeah, so it's not rounding like what we think of. Yeah, so if you think of rounding, you will say, for example, here. Yeah, so say we have pi value. Yeah, which is actually this one, and let me want say store it in single precision machine. Yeah, so that there's only 7 significant digits. So then it means that we will use only that value. Now we see here that the one that is going to be removed is from 6 up to the back here. And if we do rounding, so usually if it's above 6, for example, so we round it up. Yeah, so that if we do rounding, so that should be pi 3.141593. Yeah, so this is if we do rounding usually. Yeah, but most of the machine usually only chopped it. Chop means just cutting, just cut this value and then omit it. So that if, for example, if we chopped it, yeah, so then pi value will be 3.141592. So the error here we see is quite large compared to if we round it. Yeah, if we round it, so 3, here we have 0.00 and so on. Yeah, so we see the error, yeah, is larger when we do chopping, and this is most commonly done by the computer. Yeah, why we do chopping? Because it's faster. Yeah, if we do rounding, it means that we have to do selection. Yeah, we have to check the condition whether this is higher or lower, and then we do selection. Yeah, so that will be a computational overhead. So that's why it's faster if we do chopping. Yeah, and this is what usually performed by the computer. Now, if you look at the error here, it looks small. Yeah, but if, for example, we do thousands of calculations in this, and this error will be carried over, so you can imagine that this will be multiplied. Yeah, so that what is initially looks very very small error, later on it will be accumulated and it becomes quite significant in the calculation. Okay, so that is the difference between rounding and chopping. Okay, is there any question?
Ma'am, I want to ask a question.
Yeah, Atim, please.
We know that the relative approximation error, the equation is the new value minus the previous value over the new value, and then I think it is dealing with the precision, ma'am. So if the error is low enough, that the value is precise enough. Yes, ma'am. Is that correct, ma'am?
Yeah, so it's correct. Yeah.
And then my question is how to know the value is accurate enough and not biased, since we have no true value in the calculation, ma'am.
Yeah. So so that is there's a limitation. Yeah, because ideally we have the true value so that we can find we can get the accuracy. Yeah, so if we look at this, new value minus old value over the new value. So yeah, this is very relates to the precision. But yeah, how can we calculate the accuracy? Yeah, so we cannot get the accuracy from here. Yeah, it is true that we cannot get accuracy from here. So yeah, in this case, yeah, you are correct. Yeah, you are correct. In this case, this is more a representation of the precision. Yeah, a more representation of the precision is that the solution is getting to the same value. Yeah, so it is correct. Yeah, so without the true value, we cannot find the accuracy. Yeah, we cannot find the accuracy. But later we will see, again, because we know that dealing with error, we have rounding error, yeah, and we have truncation error, yeah. If, for example, we calculate this one, yeah, the approximate error here, yeah, so it's more related to the rounding error as what you said before, yeah, it's more related to the rounding error. But you should remember that the total error as well, yeah, the total error or the true error as well, it's also relates to the truncation error, yeah. So say we don't have the true value, yeah, we cannot find the absolute error, yeah. So we cannot find the absolute error, but we can try to minimize it, yeah. We don't know the absolute error, but we can try to minimize it by using higher order accuracy. Yeah. So yeah, it is correct. Yeah. So if we use this approximation, we don't have the truth. The true value is not really it's not really a representation of the accuracy. It is correct. Yeah. But then how can we make sure that our method is accurate enough? Is that by looking at the truncation error. Yeah. So if we look at the truncation error, so that we can increase the accuracy by choosing higher order scheme. Yeah, higher order scheme. So that is one way. Yeah. So if we don't have, say, we don't have the true value. So what we can do, yeah, what we can do is actually we can also compare it using this method. Yeah, we can also using this method, but by comparing the method which is low, yeah, say the old value is low order, compare it to the high order. Because we know if we use high order scheme, which is more complex equation to approximate, it will lead to closer solution, yeah, to the true value. Yeah, so that aside from iteration, we can also comparing this one between the result of numerical method using different scheme. Yeah, so that is one way as well. Yeah, so comparing, for example, higher order scheme to the lower order scheme. And automatically, if we choose higher order scheme, the level of accuracy is increasing. Yeah, we will see later. So that in this case, we can also minimize the error by minimizing the truncation error, which is, this is really relates to the accuracy of the numerical analysis. Okay, so that will be the answer. Yeah, is it understandable?
Oh, okay, got it, ma'am. Thank you very much.
Excuse me, ma'am. There's something. I want to make sure from the discussion, the previous discussion about the error definition. So when we have obtained the absolute error, we don't have to calculate the approximate error, or I mean, so we only have to use one of the calculation for the reference, ma'am. I mean, we only use the absolute if the absolute error is not always. Maksud saya di sini ketika error absolutnya itu tidak ada, berarti di sana kita baru menggunakan yang relatif errornya sebagai alternatif. Apakah seperti itu?
Okay. Yeah. So yeah, I get your question. Yeah. Okay. So yeah, the best way is to calculate the absolute error. Yeah. So if we have the true value, so that will be the best practice to calculate the absolute error. Now, if we have the true error or the absolute error already, yeah, we have calculated this one. Now the question is, do we still need to calculate the approximate error? Yeah. So if this is already suitable, this is already sufficient, so that will be enough. Yeah. You don't have to do the calculation with approximate error. Yeah. But you will see in some more complex cases, yeah, sometimes we need to do both. Yeah. For example, in CFD, we need to do validation, which is relates to the calculation of true error, yeah, the calculation of the relative true error. And also we have to do the calculation of this one. For example, if we want to do grid independency tests, yeah, so that is for further, for more advanced yeah, can you wait for a while? I think there is a problem with my Wi-Fi. Please wait.
Okay, ma'am.
I think it's okay, ma'am.
I think it's okay, ma'am.
Excuse me, ma'am. Your audio still mute. I'm sorry.
Okay. Yeah. Thank you. Thank you. Sorry. Okay. So. Okay. Sorry for that. Yeah, I will have to set up the Wi-Fi again. Okay, hope this will be no problem. Okay. All right. Yes. Thank you for waiting. Yeah, we will go back to the slides. Yeah. So when we talk about round of error, yeah, we will see how this will affect the subsequent calculation. Yeah. So for example, here we have addition. Yeah. The problem with addition is that this is like a very simple operation, yeah. But for example, we want to add 0.1557 times 10 to the power of 1 plus 0.4381 times 10 to the power of minus 1, for example, like this, yeah. So that what computer does is to equaling the exponent first. Yeah, so equaling the exponent. So for example, we have this one. Yeah, so this is 10 to the power of minus 1. So that it should be changed into 10 to the power of 1 and then do the summation. Yeah. So that what happened after you do the summation, for example, here we have 0.16. Yeah. And that should be 0081. Yeah, so this is the result. But what happened when we chopped it? For example, we use only 5 significant digits, for example. So we will chop the rest of here. Yeah, so we only have 0.16001. So we see here that it's further chopped. Yeah, so perhaps this value is already chopped. Yeah, this value is already chopped before, and then it's further chopped again. Yeah, so we will see here there's many times of chopping. Yeah, during the operation. Again, for example, this one, if we want to do subtractive, yeah, or we subtract this value from another value which is very close, yeah, subtracting numbers of almost equal size, so that there will be too few significant figures left. For example, here we have 0.7642, and we should remember that this value is already chopped before. Yeah, so it should contain more value there, but it's already chopped. And then we subtract it with 0.7641, yeah, for example, and this value is already already chopped. Yeah, and then we will have the value of 0.0001 times 10 to the power of 3. And then later when we will use this value, sometimes we will change the exponent value. So when we change the exponent value, for example, to the 10 to the power of 0, so that this value will go to the front, and what we have at the back will be 0 value, which is this is not actually correct, yeah, because this might have a previous value before, yeah, which is chopped, and this one as well, and the subtractant of this one is not 0, yeah, but then because we change the exponent, so that this will be the result, and this is incorrect. And also smearing. For example, we do summation, yeah, in which we have different value. Yeah, so we do summation. We have different sign every time we do the summation. In which smearing this occurs when individual terms are larger than the summation itself. Yeah. So for example, we have this series e to the power of x. So this series can be calculated by 1 plus x plus squared x over 2 factorial plus x to the power of 3 over 3 factorial plus x to the power of 4 over 4 factorial, and so on. Now with 7 decimal digit accuracy, so this is approximately 7 bits, not 7 bits, 7 significant figures, yeah, which is in 16 bits, yeah, for example. So that if, say, we want to compute up to 45 terms, yeah, so this is 1, 2, 3, up to 45 terms. So what we have as a result to this value, which is e to the power of x using the series, it will be minus 6.269 times 10 to the power of minus 5. Well, the exact answer of this value will be 4.54. So we see here that this is very significant. Yeah, the answer is incorrect because it's actually positive, but what we have in the result is negative. Yeah. And what is the source of this is because that we have the largest intermediate terms, for example, the 9th and the 10th here. Yeah. So we have the value which is very large and larger than the summation itself. Yeah, and we do subtraction. Yeah, and this value is almost similar. Yeah, so that, yeah, this is an example in which it looks like very simple. Yeah, very simple. But it's not something that we can take it for granted. Yeah, because eventually it will be accumulated, and it will give an incorrect result. Okay, so those are the example in which we should take into consideration when we do calculation using numerical method. And this one also applies when you do calculation using this method by hand. Yeah. So for example, you will have an assignment or a quiz or exam, for example. Yeah, I have seen many of the students use very few significant digits. Yeah. For example, only 2 digits on the decimal. Yeah, only 2 digits on the decimal. And when we are using very few digits, the problem is that sometimes the calculation becomes unstable. Yeah, it won't converge. Yeah, and the error is also large. Yeah, so that those are the things that we should remember, so that if we can store more significant figures, I would suggest you to use more, yeah, in order to get better solution. Yeah, and also usually it's faster. Yeah, so if you include more significant figures, the calculation also will be faster to converge. Yeah. Also, if we have inner products, yeah, so we're calculating such as this one, the summation of xi times yi, like this one. This is prone to rounding error, so it's better to use double precision in this type of calculation. Yeah. Okay. So that is about rounding error, and we have seen that the effect, yeah, it looks something that's very small, yeah, but the effect can be significant. Now we will go on chapter 4, which is about the other types of error, which is called the truncation error. And we have discussed this, yeah, that it comes from the simplification of the formula of the mathematical model that should be solved. And we will see that this is related to the Taylor series. Yeah, so I think you have learned this Taylor series, and we have discussed in the first week as well. Yeah. You found this, for example, in fluid mechanics as well, this sort of approximation. Now we will learn more detail on that. So truncation error is the error caused by the nature of numerical method that we use, yeah, to approximate the solution. Yeah, simplification that we use. So say here we have another type of series, yeah, which is called Maclaurin series. And what is the meaning of Maclaurin series? You will see, we will discuss as well later. Yeah. So this is actually one type of Taylor series. Yeah. This is also included in Taylor series, but one type of it. So it's called Maclaurin series. For example, we want to find the Maclaurin series of the equation of e to the power of x, in which we see this equation before. Yeah. And we see the effect of rounding error, that we have a very wrong result, which should be positive, the result becomes negative. Yeah. So we see here that this is Maclaurin series, and say we don't want to be too detailed in calculation, we want to simplify it, so that this function now is approximated by only 3 terms, say like that one. Yeah. So if we want to use as much as term as possible up to infinity terms, we will get the exact solution. Yeah, we will get Eventually, we will get the exact solution. But because we want to simplify it, so that we cut the rest of the term here. So this becomes the truncation error. Yeah, so we cut the terms that should be included in the calculation, but because we want to simplify it, we cut the equation. So this is the truncation error. Yeah. So if you look at this and say this is the exact solution. Yeah, if this is the exact solution, analytical solution, yeah, we can get that from calculus. Yeah, we have the graph, for example, exact solution. So this becomes the approximated solution. The approximate solution. Because in numerical method, we only use very simple terms here. So this is the approximate solution. So what will be the error here? So this is the truncation error. So you will see here that the absolute error, yeah, later also, yeah, most of the contributor is from the truncation error, also from the rounding error. Yeah, in which the effect will be dominant in the truncation error. So you will see here, yeah, dominantly in truncation error here. So that following the previous question, what if we don't have the true value? So if we don't have the true value and we want to compare the results, so try at least one result using more terms comparing with less terms, yeah, with the method that using less term or less accurate method with the more accurate method. That is one way, yeah, to compare. Because we will see later that by, for example, in some cases, adding more terms will not affect the overall error. Yeah, so the error is already low. Yeah, the error is already low. So sometimes you don't need as much as complex that one. Yeah, so sometimes we don't need more terms. Yeah, but we can limit that terms into several terms, and that will be acceptable already. Yeah. Okay, so this is the definition of truncation error. So the truncation error is the error, the equation that we don't use, the equation that we removed from the mathematical model. Yeah. Okay, so that we will apply that for the general Taylor series now. Yeah. So for example, here, this is the marching problem as what we have in the parachutist. Yeah. So say we want to predict the value of a function at point forward, which is xi plus 1, based on the value of the function and all of its derivatives at point xi. Yeah, so this is the same problem as we have before in parachutist. Yeah, so we will start. This is called the marching problem. Yeah, marching, it means we go forward. Yeah, marching problem. So then we start with 1 point. Yeah, we start with 1 point here, for example, and then we will use the information at point I here to predict the value after. Yeah, the value after I plus 1. When we have this value already, we have the function, we have the derivative, so that we will use this value to predict another point after, and so on, so that we will get the total graph. Yeah. Okay, so this is based on Taylor series, so that if we want to approximate the value after, yeah, so that the value after will be equals to the value at I plus h, which is h is a step size, times the gradient, the first derivative, plus h squared over 2 factorial plus second derivatives plus h to the power of 3 over 3 factorial times the third derivative at xi plus and so on, plus h to the power of n over n factorial times the derivatives of n derivatives of xi plus rn. So rn here is the remainder, because we know that this will get to the exact solution up to infinity. But it's not possible to get up until infinity term, so that we use the Rn here as the remainder. Yeah. So what is the remainder? Yeah, so it will be hn plus 1 over n plus 1 factorial times the derivatives, the n plus 1 derivatives of epsilon. What is epsilon? Epsilon is any value in between xi and xi plus 1. Yeah. So this is how to calculate, this is the general form of the Taylor series expansion. So that if we want to be very accurate, we will use very long calculation with much terms included. But this is not effective as well. Yeah. So what we do is that we can simplify it. Yeah. So it's all about simplifying the equations. So if we have zeroth order approximation, it means that we will use n value will be equals to 0. Yeah, n value will be equals to 0. It means that we only use the first value here, and we truncate the rest. Yeah, we truncate the rest. So that if we only use this one, so it means that the new value is calculated equal. Yeah, so it's not calculated. The new value is equal to the old value. Yeah. So with zeroth order approximation, it means zeroth order accuracy, it means the new value is equals to the previous value. If we have the first order approximation, it means that we use a first order up to n equals to 1. So this is n equals to 1. Yeah, wait a moment. Yeah, so yeah, first order approximation, yeah, means up to n 1. So that means to the power of 1. Yeah. Okay, so that means we have two terms here. Yeah, we have two terms. Yeah. So that if we want to use first order approximation, it means that fxi plus 1, that will be equals to fxi plus h fx and xi, which is h times the first derivatives, plus the rest. Yeah, so that the rest will be of order h square. So this is the truncated. Yeah, the truncated will be in order of h square here. Yeah. So this is the first order approximation. And we can also increasing, yeah, increasing up to second order. It means that if we increasing the accuracy up to second order, it means that we include up to n equals to 2, which is here. So that means we have 1, 2, and 3 terms included in the calculation. So that if we have second order approximation, so that we can calculate the new value, the time, the value at I plus 1, based on the value at xi, plus h times the gradient, the first derivatives of xi, plus h square over 2 factorials times the second derivatives of xi, plus the remaining, which is at h to the power of 3. Yeah, so that will be the rest, the remainder here will be h to the power of 3. And for example, we increase a lot here so that we have more terms and more terms, so that nth order Taylor series approximation will be exact for an nth order polynomial. Yeah. So for example, yeah, what is this meaning? For example, we have a polynomial equations. Say we have fx, yeah, equals to x to the power of 4 plus 3 x squared minus plus x minus 3, for example. Yeah. So we have here fourth order equation, fourth order polynomial. Yeah. So that in this case, if we have fourth order polynomial, it means that if we use up to h to the power of 4, so that the result will be the exact solution. Yeah. So that the result will be the exact solution. Yeah. So if we have fourth order, so then we use fourth order approximation up to h to the power of 4. Yeah. So that will be the exact solution. Yeah, so in this case, we know that if we don't have the true solution, if we increasing more terms, we choose higher order, yeah, we will end up with exact solution. Yeah. Okay. Yeah, but this is not something that we want to do. Yeah. What we want to do in numerical analysis is getting as simple as possible. Yeah, getting as simple as possible, but minimizing the error. Yeah, because sometimes it's not very practical to use very large term in the calculation. Yeah, so that, yeah, and sometimes we will see later that more arithmetic operation, more complex equation, it means more complex calculation, many more arithmetic operation that should be performed by the computer is also increasing the error because of the rounding error. Yeah, so we should remember in mind that we do calculation with computer. Yeah, more arithmetic operations means increasing error because of rounding error. So that we should choose the optimized, yeah, the optimized way on numerical method. Yeah. Now the optimized is not always as long as possible, as complex as possible, but sometimes we can be in between, yeah, in between of that. So yeah. So this is the approximation that we have. Yeah, so this is the illustration. So say we have zeroth order. So we see here the error will be very large. Yeah, of course, this is zeroth order accuracy. It's not accurate. Yeah, of course. But sometimes we use it for simplification. Yeah. Okay, so that the error will be here. Yeah, so this is the absolute error. The absolute error. So we see that the absolute error is very large. Yeah, even if we calculate in percentage, this is more than 100% error. Yeah. Then if we, for example, use the first order error, we use the linear line, for example, here. Yeah, we have the gradient at I, and then we calculate forward. We do expansion to find the value here. So we see here now the error is reduced, yeah, but it's still high. Now we use three terms, yeah, three terms in the expansion. This should not be here, yeah. So we use three terms in the expansion. Now we got second order accurate scheme. So we see here now the error is quite low, yeah. So in this case, we see that we can minimize the error, yeah, in which this relates to the truncation error. So truncation error really connected, yeah, really connected to the absolute error itself. Okay, so that this is, yeah, so this is the explanation for the Taylor series. Now we have before the term of epsilon, yeah. Now we have the epsilon value, which is the remainder, yeah. So if we look at again back here, yeah, we look again at the equation here. So the remainder here will be h to the power of n plus 1 over n plus 1 factorial times the derivatives of epsilon, the n plus 1 derivative of epsilon. While epsilon here is any value in between I and I plus 1. So what is the definition of that? So that we can see here that actually say, yeah, say we have zeroth order prediction. So zeroth order prediction means only one term to be included so that the new value will be similar to the old value here. Yeah. And the rest here will be the error, yeah, the remainder. So that we see here that this is zeroth order prediction. And the remainder or R0 is here. Well, if we have the exact prediction, if we have the exact prediction means we have the prediction that fall exactly into the actual solution. Yeah. So the actual solution here is this curve. Yeah. So the exact prediction will predict to the correct value here. So that we will see the difference between the exact prediction and the zeroth order prediction will be R0, or the remainder itself. And as we calculate here, that we can, as if we have the remainder, yeah, so that the remainder will be the gradient of the remainder, yeah, can be calculated as this one, so that the derivatives of epsilon, yeah, so if we have an epsilon value here, it can be anywhere, yeah, the epsilon value can be anywhere between I and I plus 1, and this epsilon here will be used, yeah, or has a gradient which is similar to the slope of the remainder over h, yeah, which is the difference or the remainder between the exact prediction to the zeroth order prediction. So this is the slope, yeah. So this slope will be equals to the slope at an epsilon value here, yeah. Okay, so this is actually not epsilon, yeah. This is a psi sign, yeah. Okay. Okay, so that is a definition, yeah. So basically, it's finding the slope in which this slope will cause the the prediction fall into the actual value, yeah. So this is the definition of the psi term, yeah. Okay, so we will look at the example here, yeah. So say we have this equation from this equation is minus 0.51 x to the power of 4 and so on. So this is fourth order equations. And we will use the zeroth order up to fourth order Taylor series expansion to approximate the function, in which we start from xi equals to 0 with time step is equals to 1. And we want to predict the function value at xi plus 1. Yeah. So that in this case, we can find the exact solution directly. Yes, we just insert the value of 1 here in x, so that we get the exact solution, which is 0.2. Yeah. In this case, we have the exact solution. Now we use zeroth order approximation. If we have zeroth order approximation, it means that the new value will be equals to the old value. So if the old value is 1.2, so it means that the value at I plus 1 will be 1.2 as well. Yeah. This one. So that what is the error? The error is -1. Yeah, so very large error. Now, if we use the first order approximation, so that we use this equation in which the value of xi plus 1 is approximated by the value of xi plus h times the gradient at xi. So to calculate this one, we have to find the gradient first. Yeah, so that will be minus 0.1 times 4, so minus 0.4 x to the power of 3 minus 0.45 times x to the power of 2 and so on. So this is the gradient. So this should be have a accent, yeah, single accent sign. So this is f accent. So we insert the value of f accent at I, which is at 0. So that the value will be minus 0.25. And we use this value in the calculation here, multiplied by h, so that we have the value, the function value will be minus 0.75. Yeah. And we can also use the second order approximation here, in which you use 3 terms. Yeah. So we use 3 terms. We use the second derivatives as well. So we can find the second derivatives. We insert the value, and then we have now the error is already reduced. Yeah, the value now becomes 0.45. Now, if you use third order, it means that we add more terms. Yeah, now we have the function value will be 0.3. Now, if we use fourth order approximation, yeah, so that it will be the exact solution. Yeah, because this is fourth order equations, and we use fourth order approximation, so that the result will be 0.2. You can try that. Now the question is, how come using this one is more complex than getting the solution directly? Yeah, in this case, yeah, it's easier to get the exact solution. But we will see later that we will apply this to more complex problem in which this is very helpful. Yeah. Okay, any question?
Excuse me, ma'am.
Yes.
How do we know when we should stop the order?
Okay. So which one to choose? Yeah, which one to choose, or whether is it second order or third order is already sufficient? Yeah. Yeah, this is quite difficult to answer. Yeah, because it really depends on our computer capability. Yeah, our computer capability. Of course, if you want it to be very accurate, yeah, we can extend it up to fourth order. But using more than fourth order, yeah, fifth order, I think is still possible. But more than that is not common. Yeah, more than that is not common. Even if you do later, yeah, we will apply this in simulation, yeah, in more advanced courses, yeah. For example, in CFD, CFD is only limited, yeah, for commercial software, it's only limited to third order, yeah, only limited to third order, so not more than that, yeah. But it more accurate, more accurate built-in code. You can you can make up to fifth order accuracy, but it's not common. Yeah, not common. Yeah, because what we want to do in numerical method is basically to make it simple. Yeah, so usually second order, yeah, generally is already quite good. Yeah, so we have seen this equation, this example before. Yeah, so adding one term, yeah, adding one term here from first order to second order is already reducing a lot. Yeah, so usually you from first order and second order, you can see that the increasing accuracy is tremendous. Yeah, very high effect in increasing accuracy. But later, when you increase it to third order, fourth order, yeah, you will see the differences will be not much. Yeah, for example, third order is already closer, getting closer, but it's not too much. Now, sometimes the question is, do we want to pay the cost of more calculation with small increase of accuracy? Now, usually that will be the question. Yeah. So if we need more calculation, more resources, but only an increase, for example, the difference is only 2%, 1% or more or less, yeah, for example, we don't need to do that. Yeah, we don't need to do that. So usually the optimum is the second order. Yeah, because less calculation, but already quite accurate result. Okay, so that will be my answer, Vivi. Yeah.
I think it's very clear, ma'am. Thank you.
Yeah. So yeah, based on the question, yeah, generally first order is not really recommended. Yeah, you can see here first order is not a good approximation, but second order is good already. Yeah. Okay. Any other question?
Ma'am, excuse me, I want to ask something about the Taylor series.
Yes.
I'm still confused about the reminder, ma'am.
Yes.
What it's used for what and why we don't put in the calculation like your example before.
Yeah. So what is the remainder here? Yeah. Yeah. This is just to make you understand. Yeah, that it will give the accurate it will lead to exact prediction. Yeah. It will lead to exact prediction if we add more terms. Yeah. And in here we have this sign of psi here. Is actually, yeah, if we have the exact solution, we can calculate it. Yeah, if we have the exact solution. But if we don't have the exact solution, so that also this point is it's not it's not very easy to find. Yeah. So basically, what is important about the remainder is that the remainder will be anything that will be truncated. Yeah. So actually, is a representation of the error. Yeah. So I think that will be, yeah. So don't be too confused about this sign and how to find it. Yeah, because it's not really trivial to find it. Not very easy. Yeah, not very easy to find it. So that, yeah, at least from here we know that it can give an exact prediction. Yeah, it can give an exact prediction, although it's not easy to find it. Yeah.
Okay, ma'am. Thank you. So, for the error, we just use the ET equation, right? Yang apa? That true value minus approximation value.
Yes. So this will be the order. This is the absolute error. Yeah. Sorry. This is the absolute error. Yeah. So this will be the absolute error. If we have the true value. Yeah, if we have the true value. But according to the scheme itself, yeah, we have the scheme which is zeroth order. It means if we have increasing number of order, this is said to be the order of accuracy. Yeah. So if we don't have the true value, we can just comparing the order of accuracy. Yeah. So of course, the second order will be more accurate than the first order. So when we look at this, yeah. So when we look at this, so what is important is just to see which order is it. Yeah, which order. Is it the first or the second? And we see here that this the remainder here. So this will be R0. Yeah, the remainder. This will have the order here. Yeah. Yeah, we will see that later when we find the derivative. Yeah, so this will be the remainder. So this will be the error. Yeah. Okay. So just looking at that. Yeah.
Okay, ma'am. Thank you, ma'am. It's very clear.
Yeah. Okay. So yeah, continuing to this. Yeah. We can also define Maclaurin series, which is actually derived from Taylor series as well, but with the center of expansion is 0. So this means that it will start from xi, which is equals to 0. Yeah. So that we start with this one, so that we apply the Taylor series, which is start at 0. So we will have this equation. So for example, we have the function which is e to the power of x, and we applying the Taylor series. Yeah, we applying the Taylor series, but we do the expansion from x equals to 0. So that we remember that fxi plus 1 based on Taylor series, that will be fxi plus h time f accent xi, yeah, plus h square over 2 factorial times the second derivative of xi, and so on, plus so on. Yeah. Now here we use xi for Maclaurin. Yeah. So xi is taken at 0. So that will be f0 plus h f accent 0 plus square h 2 factorial f second derivative of 0, and so on. Yeah. So that if we use this value now, yeah, now we have the function itself, fx, which is e to the power of x, the exponential of x. Yeah. So that here we can find fx. We insert the value of 0 here. So x to the power, e to the power of 0 is 1. And then we find the first derivative. The first derivative of e to the power of x, exponential x, is also exponential x. Yeah. And the value of the derivative, if we inserted 0, the value will be 1. And the second derivatives of ex is also e to the power of x. And the value of 0 is 1. Yeah. So that we will insert this. Yeah. So that we will have 1 plus we have h time 1. Yeah. H here. So h will be xi plus 1 minus xi. So xi plus 1 is x, I1 is 0. So that we will have x plus x squared over 2 factorial times 1 plus and so on. So this we will have this equation. Yeah. Okay. So that if we want to do truncation, yeah, we can choose whether we want to use 0th order, first order, or second order or third order. So we will see here the example. Yeah. So this is the result. Yeah. Okay. So we have the actual solution here, which is the blue line, the light blue line here. So this is the graph of exponential x, or e to the power of x. Yeah. And if we use 0th order, sorry, not 0th order. Yeah, correct. 0th order, which is only this one. Yeah. So that this value will be equals to 1. Yeah, will be equals to 1. So this is the 0th order equation. All one value. So you can see that the error is very large. Yeah. Now we continue on the first order. It means that we get into f first derivatives here. So this is first order. It will be a linear line of 1 plus x. So this is the value 1 plus x. So you see now, yeah, we have an error still. Yeah, we have the error, but it's getting closer. Now, so the second order equation, yeah, the second order equation means we take up to h squared. So up here, so we have 3 terms included, or we have quadratic equations to approach. So quadratic equations, second order equations, yeah. So we see here that it's getting closer already. So you can extend to third order and fourth order and so on, yeah. And including more terms, we'll get into the actual solution, to the exact solution or exact prediction. Yeah. So this is the example. Yeah. So we see here that this is already good enough. Yeah. For example, second order equations to approach exponential x. We have an error there. Yeah, but it's pretty good. Okay. The second example of Maclaurin series, for example, we have a sinus x function. And we want to solve this using the Taylor series so that we will have 0, yeah, 1, and so on. So that 0 value here, 0th order will be equal to 0. Yeah, so this will be the first order. So the first term is already the first order equations. And then we don't have the second order equations. Next, what we have, if we include 2 terms, it will be the third order equations. Yeah. So this one, if we truncate, we take only 1 term here. So this is first order. And we truncate it here, is already third order. Yeah. So that if we draw it here, yeah, so that we have sinus x here is the actual solution, yeah, the actual solution, the exact solution, the red line. And then say we have the first order, which is the linear line here. So we see that this is good accuracy here, but then in here, very large error. And if we use 2 terms, yeah, 2 terms in the equations, the first and the second terms, now it will fall into third order accurate scheme. So this one is third order accuracy. Yeah, third order accuracy. So we see here that is good enough here. Now there is a difference here. Increasing to 3 terms in the calculation. Yeah, so you have 1, 2, 3 terms. So this becomes 5th order accurate scheme. Yeah. So we see here that is getting closer. Yeah. So this is the example of doing simplification to a very difficult problem. Yeah. Okay. So in this case, it's still easy. Sinus x, you can get it directly. Yeah. Now the problem is when we want to find the derivatives, yeah, it's not very easy. Yeah, if finding the function, I think it's quite easy, but the problem is finding the derivatives. So sometimes we have the value of xi, we have the data of xi and xi plus 1, but we don't know the derivatives. So what can we do? Yeah, we want to find dfx, yeah, a df over dx. Yeah, finding the derivatives. So for example, this one. We have function which is too complicated. So the function is this one, 2 plus cos 1 plus square root of x. So we have x under the square root here, and then under the cosine sign. And then we have square root of 1 plus 0.5x. And then we have x here as an exponent, e to the power of 0.5x. So how to find the derivatives here? You might need a few days, yeah, to finish it. Yeah. Or for example, if we have, say, we have the data from experiment. Say we do several experiments from, for example, from experiment 0, 1, 2, 3, and 4. And then we have the x value, and then we have the function of each of the x value there. So then we want to find the derivatives. We don't have the function. We don't have the trend for this. We don't have the function, but we need the derivatives. For example, at some of those points. So how to calculate that one? So here we can use the Taylor series expansion now to find the derivatives. Yeah. To find the derivatives here. So what we can do is that we can truncate the equation, for example, here, and then we take this value as the derivatives. Yeah, so that, for example, we want to find the derivative of xi. Yeah, so that will be equals to fxi plus 1 minus fxi over h. Yeah. And this will be the basis when we calculate the parachutist problem as before. Yeah. We don't have the gradient. For example, previously, we need to calculate the gradient of dv over dt so that we approximate it with what? Yeah. So this is actually taken from the Taylor series expansion. Yeah. So the differentiation here that we had before, we take it from phi at ti plus 1 minus phi at ti over delta t, which is ti plus 1 minus ti. So this is similar to this one. So actually, the simplification that we have before is the first order approximation from the differentiation from the Taylor series. Okay, so this is how to calculate the gradient if you don't have the information of that. And also the Taylor series can be expanded backward. So this one we expanded forward. We want to calculate the value at xi plus 1 based on the value at xi. But we can also expand it backward. So for example, we want to find the value at xi minus 1 from the value that is known in xi. Yeah, for example, like that. We can also find the derivatives based on the expansion backward. So say we truncate these terms, yeah, the rest of the terms here, so that we can calculate the gradient of xi here will be equals to fxi minus fxi minus 1 over h. It means that if we want to calculate the gradient at point I, we have a point here I, and we have another point I plus 1, and we have another point I plus I minus 1 here. So we can, for example, connect the line from I to I plus 1, or we can approximate it by I to I minus 1. So this is called the forward approach, forward scheme, and this is called the backward scheme. Yeah. So this is how it looks like. Yeah. So say we have a function, a real function, which is shown by the gray curve here. So that if you want to find the derivatives, the derivatives at point I, so this will be the true derivatives. Yeah, the tangent line. Now, based on the backward scheme, so we connect that point with the point at I minus 1. So this will be the approximation. So you can see here there is a deviation. Yeah. So this is the deviation, and that will lead to an error. Yeah. Now the question is, which one is better? Whether we connect, for example, the line after, the point after, or at I plus 1, for example. If we connect the point at I plus 1, from I to I plus 1, so this is the derivative that we get. So which one is better? Now that is the question. And the answer is not always obvious. Yeah. Sometimes when you use forward, it's better than when you are using backward. Yeah. But on other case, depends on the curve itself, sometimes better when you use backward scheme compared to using forward scheme. Yeah. So this is why, as we said earlier, last week, yeah, we said that numerical method is an art because it's not very clear which one. Yeah, so we have to, yeah. If we look at the graph here, perhaps we can have an imagination of which one will be better, yeah, to be used. Okay, so that if, for example, we use the backward scheme, as I said before, this will be truncated, yeah. So this will be first order approximation, yeah. We use only two terms there, yeah, two terms, and then here we truncate it, so that we see the truncated here will be of the order, yeah. So if we have large O here, it means that the order, yeah, the order of h square, yeah, order of h square. So this is a truncated term. But later when we calculate the derivatives here, all will be divided by h. So this one will be divided by h, and this one will be divided by h as well. So we see that the final value for the derivative itself will be at the order of first order. Yeah. So we see here that it will be first order error, or we can say that as first order accurate scheme. So if we have these equations, so how can we see what is the method? So this is called the backward scheme, first order. Yeah, first order accurate backward scheme to find the first derivatives. Yeah, first derivative, first order backward scheme. So that we can apply the data that we have before. Yeah. Say we want to calculate the value here, the value here. We want to find the slope, the first derivative at xi here, which is at 1. So that we can calculate using backward. So that means connecting that point with the point before. Yeah. So that we have 4.1 minus 2.3 over 3 minus 1. So that will be 2. So that the first derivatives will be 0.9. And the order of accuracy is first order. We can also apply first order, yeah, in which this is similar to the parachutist problem. So to calculate the gradient is using the point forward, yeah. Or another method is using two-sided, yeah, two-sided. What is meant by two-sided? It means that to find the derivative here, we don't use the value of I itself. Instead, we connect the point before, which is at I minus 1, and the point after, which is at I plus 1, and we connect with the line there. So this will be the gradient, the approximation that we use in I. Yeah, it means that this approximation will be parallel to that. So we see here that it's getting closer to the two derivatives. So how can we get this one? Yeah, from visual we know that. So this is actually, so this is actually delta y over delta x. So delta y will be f. This one is fxi plus 1, and that one is fxi minus 1. Yeah. And delta x will be 2h. So this is how we get it. Yeah, we can see it from the graph. But how can we derive it from the Taylor series expansion? Is actually we do subtraction. Yeah, we do subtraction from the backward scheme to the forward scheme. Yeah, so that we do the subtraction. Yeah, so that say we have this one, xi minus 1, that will be equals to fxi. I rewrite this one. Yeah, I rewrite it. Minus f accent xi h plus f double accent xi under 2 factorial h square, and this is minus f third derivatives h to the power of 3 over 3 factorial plus and so on. So that we do subtraction, minus here, yeah, minus. So that here we have fxi plus 1 minus fxi minus 1. And this we subtract that one, so that will be omitted, that one as well. So that f accent xih minus minus, so that will be positive. So that will be 2 times f accent xih. Plus that one is 0, and this one we truncate the rest. Truncate it. So if we truncate it, it means that the order of the truncation becomes 0 h to the power of 3. So that if we rearrange the equations, yeah, so that if we rearrange the equations, so we have f accent x I hope this is clear, yeah. That will be that one, f xi plus 1 minus f xi minus 1 over, we have divided by 2h, plus the order of the truncated will be h to the power of 3. And this will be divided by 2h as well. So that we will end up with the truncated error will be of the order of h square. So that means this is second order. Yeah. So you will see later that using almost the same amount of arithmetic operations with the forward or backward scheme, we can have better accuracy here, which is second order. Yeah. So central, this is called to be central difference because the point itself is at the center. Yeah. Central difference, second order scheme. Yeah. Second order accurate. Okay. Okay, so we will extend forward, yeah, next week about other method available. Okay, any questions?
Can I ask a question?
Yes, Farhan?
What will happen if we choose xi not to be 0, man?
Which one xi not to be 0?
Uh,
In the Maclaurin series.
yes.
Or in this case, it can be any value, yeah. It's not necessary to be xi equals to 0. Yeah, it can be any value. So you can, for example, take this as xi. So we see previous example, yeah. So xi here is not 0. So we can choose any value, yeah. So it's not necessary to be 0.
Okay, thanks, man. I think it's clear.
Yeah. Okay, any other question? Okay, so if there is no questions, yeah, I think this is the end of the class. Yeah, so we will continue again next week, still on the same about Taylor theorem, but we will extend it, yeah, to find the derivatives of higher order. We will see that we can extend to second order for the other schemes as well, or others, or also third order, yeah, fourth order, yeah. We will extend the method to higher order scheme, and we will see how you can calculate that one. Okay, so I think that will be all for today. Thank you, and I close this class. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.